Hi, for those who don't know me, my name is Xiaoji Chen. I am on the technical steering committee of Vis.gl, or in general, the open visualization work stream for OpenJS Foundation. Together with me on the steering committee are Ib, are there, Alex, and Chris, who also organized this whole thing. Thank you. To start the day, I would give everyone an update on where we are in the development of our frameworks over the last year since the last meetup. We continue to maintain our suite of visualization frameworks. The primary one everyone knows of is Vis.gl, and based on Vis.gl, we build different types of applications. We have Kepler.gl, that is the code-free drop-in slider visualization designer. We have Hubble.gl, that is the animation or video making framework on top of Vis.gl, and FlowMap that specialize in rendering network and graph data. And supporting Vis.gl, we have Loaders.gl, that is the render agnostic loader writer software that we develop on the side that support all different formats, and we pipe them through a standardized interface that can be easily consumed by Vis.gl, but it can also be used by other applications. Luma.gl is the GPU API wrapper. We will have more details on that later. Math.gl and Probe.gl are all like very small independent modules that handle different aspects of things. Munir is our own wrapper of, if you're familiar with gesture recognition, of Hammer.js, but it has recently been some development steering away from that. And there are Python bindings, PyDeck, and Jupyter widget that allow people to use Vis.gl with Python. Right now, we have two base map libraries, React Map.gl, that let people use Mapbox.gl or MapLibre.gl with Vis.gl. And we have a package React Google Maps that is wrapper of Google Maps in React that have very similar API structure as React Map.gl, and specifically designed to work seamless with each other. The packages marked in blue here are new from this year. We have been doing some work on this repo called Vis.gl Community. Is where we put code that are not full-time maintained by Vis.gl contributors, but we feel there are potential that community can contribute to and maybe someday graduate to a more official package. And then the dev tools are where we collect all the DevOps infrastructure testing, releasing, repo setup stuff, and we will talk about that in a moment. Over the last year, we released Luma.gl v9. You can see like just a quick glance of difference here. V8 was plainly a wrapper of WebGL API. When we moved to v9, it moved to a more web GPU-like interface. So you have a device, and with device, you can create different resources. And you can see we're no longer using WebGL constants there. This new API allows us to connect with different backends. As you can see here, we right now have WebGL and Web GPU backend. So we can have one code base in Vis.gl that can work with both WebGL 2 and WebGPU. And a lot of the work we did in Vis.gl that we will talk about later are moving Vis.gl legacy WebGL code to this new device API that is Web GPU ready. One thing we lost along the way is we dropped WebGL 1 support because it just does not have enough features to have an aligned interface as Web GPU. Luma GLV 9.1, there's a lot more development in Web GPU adapter and doing shader modules with both GLSL and WGSL. The standard shader modules got moved to uniform buffer and some nice debugging features. David will probably touch more on that in his talk after me. Vis.gl v9, we moved our code base in TypeScript. That was a big push. But as you can see here, in 8.9, we exposed types in a package name /types endpoint as an experimental opt-in feature. In v9, we greatly improved the types. Have a lot of class inheritance in our later architecture. It was actually not that straightforward to do, but I think a lot of it works as expected out of the box now, which is really nice. We have dropped Babel to do code transpilation. Right now, everything is just built with the TypeScript compiler, and it just outputs standard target environment. For Vis.gl v9, we also announced a new module called Vis.gl/widgets. That's our new group of out-of-the-box offerings that are HTML UIs. Before this, when people want to use like navigation buttons and full screen widgets, for example, they have to use it with a base map library. A lot of times people want to use Mapbox GL controls, but they don't really need the base map. It's a big dependency to bring in, and it's not very straightforward to work with the other Vis.gl components. And now this is the standalone module that is designed to just work with Vis.gl and does not bring any extra dependencies. And Chris is the primary contributor that work on this feature. It's designed to be highly customizable. You can style them in JavaScript with CSS classes or with CSS variables. In both v9 and 9.1, that is, I believe we are going into beta this month. What's the plan? We wanted to do beta before the summit, but yeah. We're in the last stretch of push here. We worked a lot on Web GPU readiness. As I mentioned, we have completely changed how Vis.gl interface with the GPU. Now it's through Luma GL's new v9 API that is agnostic to the rendering backend. And we had to rewrite a lot of the layers and pipelines to remove usage of WebGL only features like set parameters, like the usage of WebGL constants, and align with the new Web GPU ready API. I believe we are almost there. We are. I think the only thing we have left to enable Web GPU is we have to write an WGSL version of all the layer codes. And all the pipelines and layer themselves are supposed to work with both WebGL 2 and Web GPU. Some other features that's going to be in this upcoming release, we almost completely rewrite the aggregation layers module. It now has a fully typed and documented generic aggregator interface that works independently from layers. You can aggregate by two 1D or two-dimensional bins and use the output directly as an input to another layer. Felix here has done a lot of investigation on using aggregation layers with tile data. I know it's a big ask from the community. We have some discussion threads every other month about it, and our plan is in somewhere in 9.1's timeframe. We'll get this out. Vis.gl published before over the last year. We are now at 4.2. I think 4.3 is in the alpha right now. It has almost 1 million monthly downloads. It have official TypeScript support and a lot of improvements. Loaders, just like Vis.gl layers, has a bunch of complicated patterns in specifying different parts, moving parts of the different format supports. So that was an ongoing effort. A lot of new formats, PM tiles, GeoParquet, GeoArrow, flat GeoBuff, and one-on text. Those are upcoming or very popular geospatial formats that people want to use, and now it can directly be included and work with Vis.gl out of the box. There are more features of 3D tiles and scene graph by extension, I3S, that are now supported in the newer versions. I don't know about the dynamic vector tiling.
Yes.
Is that the slicing data into tiles on the fly?
Yeah, it's a new, so we have this new data source concept that creates, allows you to wrap a service or a cloud native the traditional loader is really just an atomic load or something, but when you want to interact with something, for instance, a tile system, we have this source where you can query for tiles, and then the source can implement that using Mapbox vector tiles or game tiles. And we also have now a dynamic vector tiles. You basically give it to GeoJSON, then it tiles on the client. So you can take a really big GeoJSON that would be, as long as you can load it into memory, but it might be too heavy to render in one block, or there's maybe too many vertices and so on. You make it that performance. Well, you just apply this dynamic vector source to it, and now you can pass that into the tile layer. Now you get a giant GeoJSON file.
OpenJS announced V3 over the last year. The whole code base is ported to TypeScript, and it now directly loads arrow data, and it supports post-processing effects. It has switched to Vis.gl as the default back render over Mapbox. React Google Maps had its initial release last September, I believe, and is now at 1.1. It offers React components and hooks for Google Maps JavaScript API, and is sponsored by Google. Its code structure and component interfaces are not the same, but very nicely aligned with GL. And if you ever need to use it, it's almost a drop-in replacement of the map component in our other Vis.gl examples. It right now is at 150K weekly downloads and has a pretty healthy team of contributors. They have a very cautious strategy to growth. They started with a minimal feature set, and focus on established patterns. And once when someone wants a new feature, they first make it as an example with custom code, and when it stabilizes, it gets moved into the core library. Some of the minor framework updates, a common theme in our development work is we have moved all our dependency stack to full ES modules. So now it works with the new Node.js import API, and also still work with the old require or CommonJS endpoint. So server-side rendering is nicely supported by the entire stack. We used to have a lot of hacks in injecting our own code or have to exclude certain packages either on server side or on browser side. That is all dropped now. Things should be working pretty seamlessly. React Map.gl, we have some new API that we contributed to MapLibre.gl.js that specifically support the React use case. We are at a point where we probably want to do a package split and just publish a new package for as a React wrapper of MapLibre. We were holding on to that because Mapbox and MapLibre were similar enough that we didn't want to copy and paste a bunch of code. But now the API has diverged, and there are some really nice APIs we want to take advantage of Libre. I think it makes sense for us to split the code base and drop all the hacky code that we have to use with Mapbox. Apple announced their MapKit.js in July. That is their first try in maps in the web. And Felix has made a proof of concept that have Vis.gl integrated with Apple Maps. I don't think they have tilting right now.
No, they don't. Not on the JavaScript version. If you use their kind of desktop maps app, then it is able to do it, but not this one. So I couldn't rule it out.
So we could consider making an official integration module if we have the right amount of demand and people willing to help maintain that library. We have an ongoing conversation with the Apple Maps team. We will see where this goes. As I mentioned, Vis.gl community repo wanted to be a welcoming home for community extensions of Vis.gl. It's less, it's a more casual setting than Vis.gl, as in things you put in there is probably not gonna break a bunch of applications out in the wild. You can probably move pretty fast. We're not going to be as strict in code reviews, but we do help maintain the repository's health in setting up tests and release pipelines. So casual contributors don't have to think about that. All the packages in there are published to the @Vis.gl npm namespace. Sorry, the Vis.gl community namespace. So they have sort of an unified semi-official branding to it. And we try to synchronize the repo with Vis.gl, at least on the major release cycles. It's currently all moved, all the codes are moved to Vis.gl v9. Right now, some notable packages there. We have an arrow layers package that are layers that seamlessly consume geo arrow data. When Kyle gets here, you made it. We'll talk more about what you did with Longboard. And we have finally forked Nebula.gl. That is the GeoJSON editing package based on Vis.gl that were left behind when we left Uber for the OpenJS Foundation. Maintained for years. It's now known as Vis.gl community editable layers.
It's not quite all of Nebula. We just took the editable layers part. There was some other React.
I think a lot of it is, yeah, a lot of it is not used in that part. Code base, anyways. I had a typo there. Should be graph layers. That package is for graph and network visualization. Some operational updates. Felix has replaced Alberto as our newest technical steering committee.
And he needs a new photo because that one is 15 years old.
We have done a lot on the securing the supply chain security for our packages this year. I think in the last 4 or 5 months, we have seen this upcoming trend of people trying to attack JavaScript web applications by injecting malicious code into NPM packages. If you haven't been following the news, Polyfill.js basically traditionally we're telling people to include their script from a link on their own domain. So Polyfill.js or something like that. It's the same thing a lot of packages are doing, D3, but the maintainer sold the whole project and they went to a Chinese company who were found to be injecting malicious code into the script that was serving from that endpoint. It is not an isolated instance. It's very concerning. We had OpenJS Foundation also had its own observation of people trying to get into the maintainer role of a package with malicious intent. They try to talk to contributors of the project and try to show that they are willing to contribute, and they even made some PRs that are perfectly fine. This was seen in the Log4j incident last year, that they eventually would make some contribution with obscure code and a binary text file that will eventually make its way into the built and published package. It is an hack method that has been employed and observed in many cases. And although we think JavaScript running in browser is in a sandbox that's somewhat more secure, it is not immune to these things. And from Vis.gl side, for the last few months, we've been trying to tighten down security. We have been keeping a pretty close eye at who have publishing rights to our packages. All our packages have now moved to pattern where we will control the will control who have access to be able to push tags and push to certain release branches, and all the releasing itself, the building and the publishing of the packages are done on GitHub Actions in the release pipeline. So it's completely independent from local development setups and the security on someone's own laptop. We're hoping this is going to help us maintain the trust from our users that we are not going to be the victim of such an attack. I know a lot of people use this in production for like commercial products or very public facing applications that a lot of people access, and we want to make sure that we don't end up on the news like that someday.
Yeah, is there a way to increase the volume a little bit?
Sorry, I'll just try to talk louder. I don't think this is the remote. When we first joined OpenJS Foundation, we were put in the incubation projects list. That is where they have new projects that they are still watching and thinking that may have potential. We are in the process of graduating from that to the at-large projects to join all these fine open source packages that everybody's familiar with as one of the more healthily maintained OpenJS projects.
Yes. Sure, it's recorded. All right, so so you can see all the progress we made, but obviously we're not done yet, and so we have roadmaps and giving you some glimpses of our current priorities. Well, so you've seen we've done a tremendous amount of work on web GPU support and web GPU readiness and so on. So we are final stages to get production levels for the entire stack. Kind of a quick kind of recap and forward look. So in Xiaoji V9, obviously the huge lift was to rewrite in V9 and create an API that could be compatible with web GPU and yet portable with WebGL 2. And we started adopting that in then in Xiaoji V9.1, which as you mentioned, we're just getting ready to put into beta. After that, we have refactored all the WebGL specific code in Xiaoji V9, and it's there's a number of different things involved in that, but the overwhelming one has been the transition to uniform buffers. So in WebGL, you have this unit as well. So that's been a huge deal. And the remaining thing, as Xiaoji mentioned, that we'll continue with hopefully in a fairly fast follow, Xiaoji V9 2, is to get all the shaders in Luma. This is basically ready, but in Deck we need to support all the layer shaders to the new WGSL shading language that WebGPU requires. Once we've done that, we should be able to flip on the WebGPU backend and have DeckGL layers run on WebGPU. And now the fun starts. So in DeckGL V9.3, we can then really dig into the performance. I'll come back to some of the opportunities we have there. And one of the most exciting things is obviously the compute shaders that give us vastly more capabilities than what we can do with the transform feedback in WebGL. So some of the things that we look at there is they provide compute shaders. In a transform feedback, you can really only work on one row or a table at a time, but in compute shaders, you have something called storage buffers, and you can read those with random access in the shaders. So you can really implement a completely different class of algorithm, not something that just processes rows in parallel. But you have something called indirect calls, which means that you can control some of the parameters for the next compute shader or rendering. You parameters right into GPU buffers, so you don't need to read the values back from the shader and then do a new draw or compute call. with new parameters and so on. You avoid that. You can keep everything on the GPU and chain things with completely different level of performance. There's a feature called atomic writes, which means that you can have, if you think about how shaders work, they run massively parallel, hundreds of thousands of shaders at the same time. Now that becomes a problem if you're trying to update, accumulate values, and so on. You know, today we're restricted to certain blending techniques for doing that, but in WebGPU and Vis.gl, you have something called atomic writes, and that basically allows you to synchronize the writing shaders. So again, opens up a new class of algorithm. One of the biggest limitations of WebGL is that read back from the GPU is synchronous, and so every time you read something back, you get the GPU stall. Well, in WebGL, we have async read back, so that other danger should. And yeah, there's compute shaders, and they have concepts like work groups, so where you can start to communicate between different shader instances, and there's a lot of configurability and optimization you can do. So some of the ideas, and I think this is, really only our imagination that limits us, but you could do Mercator projection, in a compute shader. Today it's done in the vertex shader, every render call. There's even ways to implement general projection. So if you think about the WKT CRS, the well-known text specification format for projections, it's actually possible to write a shader from general coordinate transformation based on that. H3, we potentially do the projection of H3 indices into longitudes and latitudes on the GPU. For table processing, as long as the table is in binary columnar format, we can create, a growing library of compute shaders to do that. So tons of exciting. Advanced rendering. We use a lot of instanced rendering, but you're a little bit limited because you always have to process all the instances. There are some exciting techniques in WebGPU where you can use a storage buffer to filter your instances, and so you can kind of reduce them down in one compute shader, and then we work on the ones you need. We now have support for multiple render targets. We have integer textures. We have a proof of concept, which maybe some of you know. We have a color-based picking in Vis.gl, and because we only use one, RGB 8-bit, 32 bits, we're limited to only picking 256 layers. So we use the top of that, but now we can, use multiple render targets. We can use intra-diffuse textures, and so we can pick, billions of objects in billions of layers, and really the limitations disappear. And we're going to get massive CPU. You mentioned this last year. Cloud native is, to me, the big revolution that's ongoing in geospatial right now. So especially these cloud native geospatial formats, they're very optimized for cloud storage, which is S3 and GCS and Azure and so on. And it's notoriously reliable, cheap, many of these good advantages. So there's an explosion of formats that take advantage of these techniques, typically very large files. Then you read pieces in range request, HTTP range request. And so we're working through this. As you can see, we made quite progress on these formats, and we continue to work along this line. And new formats are emerging, so it's just an ongoing saga. And this is a very long arc of work, and I particularly excited about. So in Vis.gl, in the first incarnations, it was very much oriented towards JavaScript tables. You pass in a JavaScript table as a data property to your Vis.gl layer, and then Vis.gl runs its code using your configured accesses and so on. It transforms it into binary. That's all fine, and that will not be going away, but the idea is to, and there is now, then we've grafted on a binary interface, so you can provide, binary data, but that the interface is a little bit hacky, but maybe finicky. And now, we will have the idea is that these layers will be binary data first, binary data with our citizen, and we will make it really easy to use. Maybe potentially have native support for Apache Arrow data, and then there will be, some kind of addition on top of that can handle tables, but transforming them to binary. And when we're down on the internal layer level, everything would. So loaders kind of continues on that arc, and the loaders are more and more outputting standardized binary columnar data, having that as an option, or in binary formats that will be completely standardized, and it will work seamlessly with Xiaoji Chen.
I added that slide. So one thing that was blocking us from making Vis.gl work more seamlessly with binary tables was that we have to do data repacking. So for example, if you look at all the Vis.gl layers, we pack the vertex positions in the format of XYZ, XYZ. It's somewhat an arbitrary choice, but we can, if you have a binary format like an error table that has a column that's all X, then another column that's all Y, that's not a format that the layers can assume. And with us dropping WebGL 1 support in V9, we can actually, in the V9 timeframe, use transform feedback to repack these on the fly on the GPU. So we can use those binary columns as is without having to do additional work on the CPU. One of the big thing, at least from the core perspective, was our support for 64-bit double numbers. So if you look at longitude, latitude, 32-bit float will get you to about meter level accuracy. And when you go deeper than that, when you zoom deeper than that, you will need 64-bit float to render the geometries accurately. And WebGL and surprisingly WebGPU do not support double numbers. And our workaround is we split each double number into two 32-bit floats and send two numbers for each double to the shader. And that is currently done on the CPU. If you have done any work with optimization with Vis.gl, you know that the CPU processing, the packing of the attributes is the one thing that has the most performance hit or overhead whenever you do data updates. And we currently have a proof of concept running that's shown in this table there that does the flow splitting on the GPU. So we send in the double to int 32s and then read them bit by bit in the GPU and spit out two 32s that can be as the correct 32-bit float. And I would very much have that in the V9 timeframe, even before we support have all the official support for binary. This can be something that's opt-in for applications, and I can imagine that has a big improvement for applications that use a lot of. And of course, this will be probably even easier to do with WebGPU compute shader. And even I have talked about spinning up a new LumaGL module that just do data packing or transforming columns. PyDeck, we have been sort of out of maintainers for PyDeck for a very long time. This last year, some new contributors have come in that have picked up some slacks, and we are very excited to have Kyle talk about his project Longboard that we think is kind of the blueprint of where we want PyDeck to be, and hopefully we can have a I won't call it a merger, but a more close collaboration on designing the V1.0 release of PyDeck. A lot of the things we talked about binary is very relevant here, because in Python, in JavaScript, it's easy for you to just supply a callback, and we will choose for you whether we run something on CPU or GPU. For Python users, really write JavaScript. They process data themselves, and they give you the data, and they want the layers to just work. And all these new exciting development in geospatial formats, GeoArrow, GeoParquet, they are very well supported in the Python data science world. And to be able to directly interface with that will be a huge improvement for us. That is all I have for my session. Do you have any questions?
Yeah. How do you manage the Vis.gl1 kind of drop support in terms of the community?
We did it over a major release, so 8.9 still works with WebGL1. V9, we just announced that because the future plan to support WebGPU and no longer support WebGL1. I do not believe we have heard any complaints. WebGL2 has been universally supported by evergreen browsers since, I want to say, 2021, and Safari. iOS Safari has some issues, but I think if you just look at the generic WebGL2 support, in terms of market share, is like 96% now. It's not really a huge deal, at least, I guess, for our users.
I think I've heard one user who came back and asked about it, and I believe it turned out that he was using Internet Explorer 11, and I get my tongue, but dude. So, but yeah, we also, we got also the information. 3GS was dropping, WebGL1, and we just looked at made the assessment with all the effort that goes into web GPU and all the work that we need to do, and right for things like, because we have to move the entire code base to uniform buffers, which is supported by WebGPU, WebGL2, but not by WebGL1. We would need to spend at least a month developing some kind of system that transforms an abstract statement uniforms, uniform buffers one place, uniforms another way, and so yeah, it just didn't make sense, and it was time to let it go. Unfortunately, there hasn't been.
The most noticeable change for us is actually we can no longer run unit tests of layers in Node. That has come up a bunch of discussions and issues. Before we use headless GL, I believe MapLibre uses that too. It is not a full implementation of WebGL1, but it does work. So you can run WebGL rendering pipeline and write 2 pixels. And that was what we were relying on for unit testing for a long time. And in V9, we just moved completely to browser-based, headless browser-based rendering tests. And it's actually more flexible to us, because once we do flip the switch and enable WebGPU, we want all the layers to be tested in both WebGL and WebGPU. And that is not going to be a thing in Node.
There are Node projects that are WebGPU integration. So I haven't been tracking it lately. The Dino project is announcing it and then putting it back and then re-announcing it, and so on. But I fully expect it to come, and whenever it does, we can we can do also run tests on Node.
We also have the integration with the different base maps and different versions of base maps, and some of those are on WebGL 1, some of them are on 2. And there we have the benefit that in most of our integrations where we share the context, we can also have a mode where we're not showing the context, so we can integrate with the base map that's running a different version of the sort of browser graphics stack.
I think all at least officially supported base maps are supporting WebGL 2 at this point.
Yeah, but someone might want to be using an old version.
ArcGIS upgraded.
We do some clever
Not very
things
long ago.
with that. We hook into the get context function, and when another library requests a WebGL 1 context, we actually intercept that. We hand them a WebGL 2 context. We implement that context to its own WebGL 1 extension. Yeah.
We actually do that?
We did that with Mapbox. I think they eventually switched to WebGL 2 by default.
So we don't run on WebGL 1, but we can integrate with another WebGL library that
Expect
only built off of WebGL 1 in many cases.
I think Kepler was doing that before it switched the base map library.
Yeah.
Because we're using Mapbox v1 for licensing, and once it switched to MapLibre, that
Chris probably knows most about it. I built this.
Yeah. Oh, yeah. We do that.
But hopefully, you'll be running on a proper environment. These kind of tricks won't be expected.
So can you go back to the slide where with the 9.0 series, where you were talking about the it was no, later on, I think
Roadmap?
there was a roadmap slide around 9.0.
9.1, 9.3.
So you, yeah, there you go. Right. So I'm going here to a little bit of I obviously kind of very much support with the work that we're doing with Web GPU and so on, but it's it's taken a long time. It's been a massive effort. So thank you very much for everybody who's working on it. This has been a massive effort. But if we think it, also from a user's perspective, I feel like somehow, there's a lot of work that we are doing that is not producing very much visible results for the users. Yeah, it's an investment in the future, but I wonder what you guys think, from that perspective, because there's so much that we can, in a way, or that we should try to balance a little bit the roadmap to kind of provide benefits for the users and, an investment on long-term. And I feel like if I look at 9.0, we were not able to really showcase any value for the user to go to 9.0. 9.1 doesn't sound like it's going to have any benefit for the user. In 9.2, we might start getting some benefits, right? Also, and in 9.3, maybe finally we start getting some value for the user. And then in 10, you've actually dropped quite a bit of value for the user, right? So, I don't know what are your thoughts on this, but I think it's a little bit unbalanced. To have the entire 9 series kind of like a little bit like a lost kind of version for the user.
I don't think we are. This is hardly the only thing we're doing. We are also working on things like widgets. We're working on the refactor of aggregation layers. It's needing a rewrite in terms of functionality and TypeScript support and all of that. And it is. I personally have seen this in a lot of things I think perhaps TypeScript API or some other highly popular frameworks where you contact them and say, I'm encountering an issue, and they come back with all of our resources. It's actually investing in working on our next version. So we probably won't be able to do this and that, right? We don't want to be in that situation. We don't want to disappear on people for a year and then come back with a thing that we have hardly tested in any production environment and say this is the future. We now have the whole thing in front of you. we chose to make smaller gradual releases as we work on things. So people can test them, people can use them, and we are confident that what we're doing is not going to break what they needed to do. And when we do flip the switch, it's not like we are turning the whole world upside down. We have confidence that this thing will continue to work for existing applications, but ton of value for people who need it for the next day.
Yeah, just to add to that, like completely understand the sentiment. There's a lot of changes without a visible difference, visible new feature. But the seamless transition that we're trying to do here is, I think, a very big feature, because we could have just said, okay, Web GPU is the future, version 9 is Web GPU, everything before that is WebGL. And in doing this dual support, we've added ourselves like a lot of work, but I think we also help move people across from the old graphics API to the new graphics API, hopefully without them even really noticing there's a difference to the application.
Do you do any benchmarking? And can you already tell if Web GPU has different performance numbers?
I'll come back to that a little bit in just my talk is just on.
Okay.
We don't have any layers currently have like parity features right now in both WebGL and Web GPU, so we can't tell from like an DeckGL application level how much the performance improvements will be. I haven't in some of the slides. We have seen people report that with Babylon, not Babylon, is TensorFlow JS have reported Web GPU is about 3 times faster. Mostly because they utilize view shaders over the transform feedback and texture-based technique.
Yeah, it's a complicated picture. It's not just flipping the switch and make faster by itself, but if used right. I mean, I just want to give my perspective on this. So this this has been a very slow release cycle. So yes, I don't remember exactly, but DeckGL v9 was probably a year in the making. Yeah, 9.1 has been. We were kind of close to having it ready, if I recall, last year when we met. And then now 9.1, we're very close to having it ready. And that's not the release cadence I would like us to be. I mean, for these minor releases, I think that, you know, at least every 6 months, ideally every 3 months, we have another minor release, and we bring out some new features, some new layers, some new capabilities. And I believe that, you know, this is all the top of the iceberg that's under the water. What we have left here for 9.2 is really, yes, it's a, you know, rewriting all these shaders is a bit of work, but you know, it's something that we could do in a much shorter time cycle. So 9.2 is not another year. You know, I really expect that will be a much quicker thing. Once we get that in place, then I think we can really start investing, because I also think that many of the things we want to build on the new, you know, Web GPU way of doing things. So all that we want to build it as compute shaders, you know, we want to optimize performance based on the Web GPU architecture and all of that. And so, you know, it's a little bit of hesitation in going and building a lot of features on the old way of doing it. But so
I guess what my main problem, if I say with this, is that just like, yeah, 9.0 is a ticket year, 9.1 still is not there. We could be very easily like 1.5 years until 9.3. And then if you look at the next slide with Deck 10, some of the things that you have on Deck 10 are very, very much needed now. And if we don't act on them soon, I mean, we've seen it already with Longboard, we've seen it, you know, with, we're going to see it coming. If we don't start adopting something like GeoArrow under the hood and so on, we could be in a little bit of
I also want to remind you, you came in a little bit in the middle, so I don't know if you saw it, but we have created this DeckGL community repo, and there we're incubating things like the new arrow layers module. So it's not like we're not working, and there's a lot of work happening in Vis.gl, which is continuing to do releases and adding new formats to the ecosystem. So there's a lot of work happening there on the binary, and I think that, you know, why I say DeckGL v10 is more like, you know, in DeckGL v10, let's reimagine. Let's go back and look at the API, look at first principles, and maybe think about it, binary first, but that doesn't mean that a lot of that improved binary support can't come in minor Vis.gl releases. And then like, if we need to break the API or, to make everything more seamless and intuitive and all that, then it's in V10. So that's kind of just a label. Doesn't mean we.
Yeah, just to echo the, the comment about developments. When we make a change to core, if you look at Vis.gl core, a lot of code have been there since maybe V6, right? We are very cautious in changing the core because anything we put in there, any line of code change that could change performance is gonna affect everything that come on there. If we change how attribute is packed, it's going to like multitudes of performance overhead for every application. So we are very cautious in making changes there to the core API. We want to ask questions: are we making the right decision? Is this going to set us up for success in the next 2 or 3 major releases even? But once we have done that, and when we move to updating things to support all these new features or utilize these new features on the layer level, it is very fast. Felix did all the migration to uniform buffer of the layers. Once you figure out how to do it for one layer, you just crank it out for all the other 30 layers, right? Like it passes unit test, it renders identical to the previous version. So we are very confident that it does what it's supposed to do. There is no question there. It's the same thing for 9.2. Once we start writing the shaders in WGSL, once we've done it for one layer, we figured out how to do it. We can just have many contributors pile on it and just crank it out for everything. It's not going to take that long. It's the initial decision on what kind of interface do we want to have between Luma and DAC, and how do we implement it in a way that's efficient and generic enough for us to support both rendering backend. Those back and forth are the most time consuming, and it's if you ask me, I think that's time well spent that we have to do to keep up with the landscape of the web-based GPU.